Hello student, I am Nirmala Morade, Department of Mathematics from S.V.K.T College, Devali Camp, Nasik. Today's topic is division algorithm from Unit 2nd, divisibility theory in the integers. In last lecture we have studied mathematical induction, the second principle of mathematical induction and examples related to it. So, in mathematical induction we have to give a statement. Suppose it is denoted by Pn, where n is greater than equal some integer m. To prove this statement, we have to use the following steps in second principle. First, prove the theorem for the integer m, that is prove Pm. Second step is assume Pm, Pm plus 1, Pm plus 2 up to say Pk, and prove that Pk plus 1 is also true. Then by second principle of finite induction, the given statement is true for all integer n greater than equal m. Here m may be replaced by 1 also. So in next lecture we have studied this principle as well as the examples depending on it. Now in today's lecture we are going to study division algorithm for the integers and the related examples using division algorithm. After watching this video, students are able to state and prove the division algorithm theorem. Students are understand how to prove the uniqueness, and students are able to solve the examples using division algorithm. Now in school level already we have studied what is meant by division. So now suppose I consider an integer 39 and divide this integer 39 by 5. So 5 sevens are 35. So subtract this 35 from 39. So the remainder or the remaining is 4 here. So in this example 39 is called dividend, 5 is called divisor, 7 is the quotient and 4 is the remainder. Division algorithm is a theorem, it is not an actual algorithm, and this division algorithm gives the relation between all these four numbers a, b, q and r. So now let us first consider the example of division algorithm. So statement of the division algorithm is, if a and b are the two integers with b is greater than 0, then there exists unique integers q and r satisfying the equation a equals to bq plus r and 0 is less than equal r is less than b. So now in this statement q is called the quotient and r is called the remainder in the division of a by b. So remember here b is strictly greater than 0 since both are integer, but b is greater than 0. Now we will prove this theorem in 3 steps. In first step we have to given a and b are the integers with b greater than 0. In first step we will prove there exists integers q and r satisfying the equation a is equals to bq plus r with 0 is less than equal r. In second step we will prove r is strictly less than b, and in third case or in third step we will prove the uniqueness of the integers q and r. So let us consider the first part of the theorem. So now here first write what are the given things. So we have to given a and b are the two integers with b is greater than 0. So in first step we want to prove that there exists two integer q and r such that a is equals to bq plus r with 0 is less than equal r. So for that we consider one set S. S is the set of all numbers a minus bx such that x is an integer and a minus xb is greater than 0. So observe the set S carefully here. Here a is integer, b is also integer, and we have to consider x is also an integer. So a minus xb is an integer, and additional condition is a minus xb is greater than equal 0. That is clearly here S is set of integers or set of all non-negative integers. So it is subset of non-negative integers. Now actually to prove the first part, we will use here the well ordering principle. The well ordering principle states that every non-empty subset of non-negative integer has a least element or the smallest element. So now first, already S here subset of non-negative integers, we want to prove that it is non-empty. So show that at least one element is present here. So now for that, we consider here, first we have to given b is greater than 0. So b is an integer, it is greater than 0 means b is greater than equal 1. Multiply both sides by mod a. So mod a into b is greater than equal mod a here. Mod a is a positive quantity. As we know that for any inequality, if you multiply by a positive quantity, inequality remains the same. So that's why we get here mod a into b is greater than equal mod a. Now consider the element or integer a minus in bracket minus mod a into b. So our aim is prove that this is an integer of S or this is an element of S. So now for that I just rewrite it first. This minus minus becomes plus, so a plus mod a into b. Use the above inequality, mod a into b is greater than equal mod a. So mod a into b is replaced by mod a, so we get a greater number here. So a plus mod a into b is greater than equal a plus mod a, and as we know that a plus mod a is always greater than equal 0. For example, if I consider a is 2, its mod is also 2, so 2 plus 2 is greater than 0 here. But if I consider a as a minus 3, so minus 3, its mod is plus 3, so addition of minus 3 plus 3 is equal to 0. So here we get 0. So here a minus of minus a into b is greater than equal 0. It is an integer and it can be written in the form a minus xb, because here x is equals to minus mod a, which is an integer. So a minus minus mod a into b is an element of S. So at least one element is present in S, so S is non-empty set, as well as it is a subset of non-negative integers. So we can use here the well ordering principle. So by well ordering principle, S has the smallest element. Suppose its smallest element is R. So R is the smallest element of S. Now again see what is the definition of S. We consider S as set of all integer a minus bx, x is an integer, and a minus xb is greater than equal 0. So since R is the element of S, so first of all R should be greater than equal 0. Second thing is R can be written in this form a minus bx for some x where x is an integer. So suppose this R we consider there exists an integer q. There exists an integer q such that R is same as a minus bq with R is greater than equal 0. This is just because of the definition of S. So now here just rewrite the sentence there exists integer q such that a can be written as bq plus R with R is greater than equal 0. So our first part is proved here. Now in second part we want to prove that R is strictly less than b. This is our claim, prove that R is strictly less than b. Now we prove this part by using contradiction, method of contradiction. So for this method of contradiction, suppose our assumption is R less than b is not true. r less than b is not true. So r is not less than b means r is greater than equal b. We assume r is less than b is not true. So r is greater than equal b. Subtract b from both sides, we get r minus b is greater than equal 0. So now here consider r minus b and now put the value of r. So which is we have to already obtain. R is equals to a minus b cube. Put here the value of r. So a minus b cube minus b. Keep first term a as it is. From last two terms take minus b as a common. So in bracket we get here q plus 1. So this term can be written as a minus b times x, where x is here q plus 1 and as a q is an integer, so x equals to q plus 1 is also an integer. Okay. So if you observe here, first thing is r minus b is greater than equal 0 and second thing is r minus b can be written as a minus xb. So by definition of S, by definition of the set S, this r minus b is the element of S. R minus b is the element of S and r minus b is less than r also. R minus b is less than r also. So here r minus b is the element which is less than r and already we have to mention r is the smallest element of the set. So this implies that our assumption is wrong, or this is a contradiction to the r is the smallest element of S, because S contains an element r minus b which is smaller than r, and so this is a contradiction to r is the smallest element of S. So our assumption that is r is less than b is not true, is wrong, and therefore r should be less than b. So this completes our second step. Now in third step, we want to prove the uniqueness of both the integers q and r. So now suppose I want to prove the uniqueness of, I want to show that two integers are equal for some required things. So for that we consider, suppose the given thing, given statement is true for different values of that integer, and to prove the uniqueness, prove that two integers should be equal. That is, suppose we assume that a has two different presentation in the desired form. That is, a can be written as bq plus r. This is one presentation of a, and the another presentation is a is equals to bq dash plus r dash. So since we want to prove the uniqueness of the both integers q and r, that is we have to prove that r should be equals to r dash and q should be equals to q dash. Okay. So to prove this one, either we subtract both the equations, or we consider, or we find the value of r and r dash from these two equations. So from these two equations we get r equals to a minus bq, r dash equals to a minus bq dash. Then subtract these two, r minus r dash. Subtracting these two equations we get, first of all a gets cancelled, r minus r dash is same as minus bq plus bq dash. Take b as a common. So if you take b as a common, so remaining is q dash as well as q dash minus q. So denote this equation as a 1. So remember here r minus r dash is same as b times q dash minus q. So our next step is we take the mod of both sides. So by taking the mod of both sides here, we get mod of r minus r dash is same as mod of b in bracket q dash minus q. Since we know that b is a positive integer, so its mod is b itself. So b into mod of q minus q dash. Now denote this as equation second. So now here, since already we assume that a has two different representation in desired form, that is a can be written as bq plus r and a is same as bq dash plus r dash with 0 is less than equal r is less than b, and 0 is less than equal, r dash is less than b here. So now r is less than b as well as the r is less than b and r dash is also less than b. So obviously the mod of r minus r dash is less than b. Mod of r minus r dash is less than b. So now since this quantity is less than b, use the second equation. So b into mod of q minus q dash is also less than b by using equation second. So b is here positive integer. That's why we can use the cancellation law. Here bb gets cancelled. So we get here mod of q minus q dash is less than 1. As well as we know that mod of any quantity is always greater than equal 0. That is mod of q minus q dash is also greater than equal 0. So just rewrite this inequality as 0 is less than equal mod of q minus q dash is strictly less than 1. Is strictly less than 1. Q is an integer, q dash is also integer which is greater than equal 0 and less than 1. This implies q minus q dash should be a 0. So q minus q dash is 0 implies q is equals to q dash. So now use the equation 1 or 2. So from equation 1 we get r equals to r dash here. So this proves the uniqueness of both the integers q as well as the r, and hence the whole theorem is proved here. So just recall again what is the theorem here. A and b are the two integers with b is greater than 0. Then there exists unique integers q and r satisfying the equation a is equals to bq plus r with 0 is less than equal r is less than b. Now depending on this, let us consider one theorem which is called the corollary. A statement which is proved by using the some theorem that is called as the corollary. So this is our statement of the corollary. If a and b are the integers with b not equals to 0, then there exists unique integers q and r satisfying the equation a is equals to bq plus r and 0 is less than equal r is strictly less than mod b. So in division algorithm theorem we consider b is greater than 0 and here we consider b is not equals to 0 here. So we prove this statement by using the division algorithm theorem. So since the given thing here, first of all a and b are integers with b not equals to 0. So b is an integer which is not equals to 0. So there are two cases. The first case is either b is strictly greater than 0 or b is strictly less than 0. So let us consider the first case, b is greater than 0. So mod b is equals to b by definition of absolute value. And so we can apply the division algorithm to a and b. So by division algorithm there exist unique integers q and r satisfying the equation a is equals to qb plus r with 0 is less than equal r is less than b. But here b is positive, so mod b is equals to b itself. So we replace b by mod b. Hence our result is true here in case b is greater than 0. Okay. Now let us consider the second case. In second case we consider here b is less than 0, that is it is negative. So mod of b is equals to minus b which is a greater than 0 here. Apply the division algorithm to the numbers or to the integers a and minus b. Apply division algorithm to the integers a and minus b where minus b is greater than 0 here. So by division algorithm there exists unique integers q and r satisfying the equation a is equals to q mod b plus r with 0 is less than equal r is less than mod b. Okay. Now replace mod b equals to minus b. So the statement becomes a is equals to minus qb plus r. We denote minus q as a q dash. So q dash into b plus r with q dash is same as minus q, which is integer, and hence the statement of the corollary is also true in case of b is less than 0. So now if we combine both corollary statement and the original statement of division algorithm, then we can say here if a and b are the two integers with b is a non-zero integer, then there exists the unique integer q and r such that a is equals to bq plus r with 0 is less than equal r is less than mod b. So now let us consider some examples related to division algorithm. We consider simplest example. First one is take the division of 6 and 5 and find the remainder and quotient in this case. So we know that in case of division algorithm, q is called the quotient and r is called the remainder in the division of a by b. So here we know that 6 can be written as 5 into 1 plus 1. This is a simple division or simple expression. 6 equals to 5 into 1 plus 1. So here quotient is 1 and the remainder is 1. So let us try the same thing with the integers 61 and minus 7. That is, find the remainder and quotient in case of a is 61 and b is minus 7. So we know that 7 8s are 56. And since we express in terms of minus 7, so we can express in this form. 61 equals to minus 7 into minus 8 plus 5, where q is minus 8 and r is 5. Remember, r should be less than mod of b here. That is very important. The remainder should be greater than equal 0 and less than mod of the b. So now since here r is less than mod 7, therefore this is the quotient and remainder. Let us consider another simplest example. Take a equals to minus 2 and b is equals to minus 7. Observe all these three examples are different here. So when you study this again, compare all these three examples. So now try to express minus 2 in terms of minus 5. So minus 2 can be written as minus 7 into 1 plus 5. If you consider the left hand side, solve it, it can be written as minus 1 into 1 plus 5 is minus 2. So first thing here, quotient is 1 and remainder is 5, which is greater than equal 0, and it should be less than mod b, that is, it should be less than, strictly less than mod of minus 7, that is 7. It is true. So here quotient is 1 and remainder is 5. So now consider some examples that can be proved by using, for some statements that can be used by that can be proved by using the division algorithm theorem. So now let us consider the first example here. Use division algorithm, prove that the square of any integer is of the form 4k or 4k plus 1, where k is an integer. So now to prove this statement, we consider a and we take b as a 2. Remember this one. To prove this statement, we apply the division algorithm to the integers a and 2 here. So by division algorithm, there exist unique integers q and r satisfying the equation a is equals to 2q plus r with 0 is less than r is 0 is less than equal r is less than 2. So r is an integer which is greater than equal 0 and strictly less than 2. So only two integers are there. One is 0 and one is 1. So first put r equals to 0 and then 1. So a becomes a is equals to 2q. If I put r equals to 0 in first equation, or in a equals to 2q plus r, and then put r equals to 1, so a becomes 2q plus 1. So means if we divide any integer by 2, then it can be written either in the form a equals to 2q or a is equals to 2q plus 1. So our statement is, we want to prove the statement square of any integer is of the form of 4k or 4k plus 1. So for that we should squaring these integers. So squaring this, we get here a square equals to 2q square or a square equals to 2q plus 1 bracket square. Simplify it. So we get here a square equals to 4q square or a square equals to, now squaring the term by using a plus b bracket square here. So square of first number is 4q square plus the middle term 2 times the product of the two terms, that is 4q, and plus square of the last term is 1. So now just rewrite the second term here. First keep as it is, a square equals to 4q square, that is 4 times k, here k is q square which is an integer. So in first case a square can be written as 4k form. So consider the second case, a square equals to 4q into q plus 1. From first two terms we just take 4q as a common. So a square becomes 4q, q plus 1 plus 1. So first term is 4k plus 1, where k is q into q plus 1, which is again an integer because q is an integer. So now here we get here square of any integer either can be written in the form of 4k or 4k plus 1. Now let us consider the similar type of example, but in every example we change the value of b. So in second example, we want to prove that the square of any odd integer is of the form 8k plus 1, where k is an integer. So we will prove this statement by using division algorithm, but here we apply the division algorithm to a and 4, that is take the value of b as a 4. So now by division algorithm there exists unique integers q and r such that a is equals to 4 times q plus r with 0 is less than equal r is less than 4. Again here remember r is an integer which is greater than equal 0 and strictly less than 4. So there are only 4 integers are present or are with this condition. So 0, 1, 2, 3. So now put r equals to these values. So we get the 4 different forms of a. The first form is 4q, second form is 4q plus 1, third form is 4q plus 2, and last form is 4q plus 3. That is, when we divide any integer by 4, there are only 4 possible remainders, 0, 1, 2 and 3. And that's why a has 4 different forms. Either a can be written as a 4q, 4q plus 1, 4q plus 2 or 4q plus 3. But among these 4 integers or among these 4 forms, only 2 integers are odd and 2 are even here. So any integer which is multiple of 2 is called the even, otherwise it is called the odd. So a equals to 4q and a is equals to 4q plus 2. These 2 are even integers and remaining 2 are odd. So just we take the square of these two, 4q plus 1 and 4q plus 3. Now after squaring this and simplifying it, simplified. So a square, take the first value 4q plus 1 bracket square, use a plus b bracket square formula. So square of first number 16q square plus 2 times product of two terms. So it becomes 8q plus the square of the last one, that is 1 is 1. So we want to express this in the form of 8k plus 1. So from it is very easy. So from first two terms we take 8 as a common term. So if you take 8 as a common, remaining is 2q square plus q and plus 1 as it is. So denote the 2q square plus q as a k. So this integer a square or the square a square can be written as 8k plus 1. So now consider the second case, put a is equals to 4q plus 3 and squaring it, apply again the formula. If you simplify, we will get here 16q square plus 24q plus 9. So we want to express this in the form of 8k plus 1. So this 9 can be split as 8 plus 1. Okay, and from first 3 terms, you can easily take 8 as a common. So after taking 8 as a common, remaining is 2q square plus 3q plus 1 and this last one as it is. So again this a square can be written in the form of 8k plus 1 here, and k is 2q square plus 3q plus 1 is an integer because q is an integer here. So here also we can easily prove here any square of any odd integer can be written in the form of 8k plus 1 by using division algorithm. Now let us consider the last example. Show that the expression a into a square plus 2 upon 3 is an integer for all integer a greater than equal 1. So if you put different values of a, you can easily check whether this quotient is an integer or not. If I put a equals to 1, it is an integer. If I put a equals to 2, it is again an integer. So now let us prove this statement. So for that you can use the division algorithm. For that consider b as a 3. So we take a and b as a 3, apply the division algorithm. So by division algorithm there exists unique integers q and r such that a can be written as 3q plus r with 0 is less than equal r is strictly less than 3. Okay. Again here r is strictly less than 3, so there are only 3 possible remainders 0, 1, 2, 0, 1 and 2. Put these values in r. So a has 3 different forms. A can be written as either 3q, 3q plus 1 or 3q plus 2. Now we take these 3 different cases one by one. So first we take here a equals to 3q. Consider the given expression. Now just put the values. Just put the value of a as a 3q, simplify it, easily we will get our required result. So now first we put a equals to 3q in the expression a upon a square plus a into a square plus 2 upon 3. So replace a by 3q into 3q square plus 2 upon 3 here. Just simplify it. Actually there is no need to simplify, 3 gets cancel here. Remaining is q into 9q square plus 2, which is an integer because q is an integer, and hence in first case it is true. Now consider the second case. A is equals to 3q plus 1. Again consider the expression. Now put the values. So after putting a equals to 3q plus 1, we get this expression. Now we can't easily cancel these 3. So for that evaluate the second bracket here. So if you evaluate the second bracket, so we get here 3q square plus 6q plus 1 plus 2. Again we use the formula a plus b bracket square is same as a square plus b square plus twice ab. So if you observe carefully the second bracket, from second bracket we combine the last 2 terms, that is 1 plus 2 is 3, and we can easily take 3 as a common, and that 3 will cancel with the denominator. So this is our result, 3q plus 1 into 3q square plus twice q plus 1, which is an integer. So, okay. So we prove the result in second case also. Do the same thing for the third case, that is take a equals to 3q plus 2. Now just put the value in the given expression and simplify it. Just do this, it is very easy, not so hard. And in this case also we can easily take 3 as a common from the second bracket. 3 gets cancel. So this is remaining expression, and which is an integer because q is also an integer. So it proved our given result or the example. So apply the division algorithm to find the quotient and remainder for the division of 34 and 8 minus 8. Do this at home. This is also one of the example. Use division algorithm to prove that n into n plus 1 into twice n plus 1 by 6 is an integer for n is greater than equal 1. So we can easily prove such type of statement, but for that we will use the trial and error method. So now to prove such a statement, first we have to decide what is a and b. So in this case we take a equals to n and b is equals to 6. A is equals to n and b equals to 6, and when we take b equals to 6, we will get there are 3 cases. Apply all these 3 cases here, so we will get the required result. So do these 2 problems at home. So now let us summarize our today's lecture. In today's lecture, we have studied division algorithm for the integers. It gives the relation between dividend, divisor, quotient and the remainder. So if we have to given the two integers a and b with b not equals to 0, then there exists unique integers q and r such that 0 is less than equal, such that a is equals to bq plus r and 0 is less than equal r is less than mod b. Remember here r is definitely or is strictly less than mod of b. So here q is called the quotient and r is called the remainder in the division of a by b. Also, if I apply the division algorithm to two integers a and b, and if we take b equals to 2, then in that case there are only two possible remainders 0 and 1. So there are only two forms for a. First is a can be written either 2q form or a is equals to 2q plus 1. Similarly, if I take b is equals to 3, there are three different representation for a: thrice q plus 1, thrice q plus 2 and so on. This is a reference for your study, Elementary Number Theory, 7th edition by David Burton. See the chapter 2 and section 2.2. Additional examples also given. So solve this example as a homework. In next lecture, we are going to study divisibility of integers, its properties and some examples related to it. Thank you.